Well then, guys, recall where we left off. We talked about the simplest types of functions. So what is the simplest function possible? Remind me, please. And also, guys, turn on, unless you are in a situation where that's extremely inconvenient, please turn your cameras on. This way I recognize you or begin to recognize you and know how the explanation goes, if you understand it or not. Yes, polynomials, guys, is the simplest possible function. Now, would anybody tell me, please, why is polynomial the simplest type of function?
It's just the multiplication.
That's right, addition and multiplication. Remember, we decided to group subtraction together with addition because we're familiar with negative numbers, right? So let's say if you have 5 minus 7, it's like 5 plus minus 7, okay? So we can imagine that subtraction is already incorporated in addition. Precisely that. The next level of difficulty is rational functions. That's where we allow division. You agree? Division is yet another operation. For this purpose, we consider it as a separate operation. And then we make the observation that if you have to use division, you can use it exactly once. You remember why? Right? It's simply, I hope you can convince yourself of that. If, for example, I want to add numbers like 1/2 plus 2/3 plus 5/7. Yes, here I use division exactly 3 times, but I can find a common denominator. So I can write it as 2 times 3 times 7. Here I have 3 times 7 plus 2 times 3 times 7. That's the least common denominator. And this would be then 2 times 5. Sorry, 2 times 7. 2 times 2 times 7 plus, here we have 2 times 3 times 7. This has a 7 but doesn't have a 2 and a 3, so we have 2 times 3 times 5. Yeah, and when we add it up, we just have one division, which is 2 times 3 times 7, and whatever this is just a summation. Yes, you see, my point simply is that if you have to use division, you can use it exactly once. I hope that's clear. Good. Wonderful, guys. So then we realized, I hope you understand that when you take limits, they are very easy in both instances, especially very easy when you deal with polynomials. When you apply a limit to a polynomial, you get exactly the same thing as if you just plug in the number. Okay, so limits do not give different results for polynomials. So limit operation will give the same output as the just plugging in. Okay, and that is because, formally speaking, it's because of the limit laws. If you just apply the limit laws, you should be able to see that to be the case. Similarly, if you apply the limit laws for a quotient, then the only time there is any difficulty is when the denominator produces 0. Good? So limit of the quotient is the quotient of the limits unless the denominator approaches 0. Then you have to be more careful. Now help me with this problem, guys. Tell me, please, here, what is going to be limit as x goes to 5 of x squared minus 25 divided by x minus 5. Calculate it very fast and tell me what will I be getting. Okay, so it's v, and some people say undefined, but why is it undefined? What are you doing, guys? Are you plugging in 5? Okay, that's the question. What are you doing? Okay, think about it a little. Let's see. So some people say 5, some people say 10. One person says 1, Robert says 0. Okay, think about it for a little bit longer, guys, right? We need to be we need to move faster. All right. Let's solve it together, guys. Okay, so let's see what happens here, guys. So first of all, your first observation is that if you were to plug in 5, you would get 0 over 0, right? If you were to plug in 5. But that's not what we do. We don't plug in when we calculate limits. So we look at it. We know that if x approaches 5, the denominator approaches 0. Good? But it's not an actual 0. So its limit as x goes to 5 of x minus 5. And then I factor the numerator. I factor the numerator. Tell me, please, what's my next step?
You cancel out the x minus 5 in the numerator and the denominator.
Thank you. Now, why am I allowed to cancel it? Am I not dividing 0 by 0? I'm not allowed to divide by 0. Again, not allowed is a wrong expression, guys. I really cannot stress enough that you should understand why division by 0, it can cause problems. Why in this situation I am not dividing by 0 when I do that? Yes, exactly, Humira. When x is close to 5, x minus 5 is not actually 0. So it's not actual 0 divided by 0. So I can cross it out, right? And then I just have limit as x goes to 5 of x plus 5. And the answer is 10. Good? So if you got 10, that's all right. That's what you should be getting. So those functions, rational functions, are only troublesome when you take limits and divide by 0. Otherwise, you can just plug in the number and you will get the same result as if you took the limit. Good. Here is another question, guys. Now, do you see this question on the board? So 3 plus h squared minus 9 over h. Please calculate the limit as h goes to 0. Okay, a few of you have the right answers. A small question. A person by the name of Artikov Sharuz. Is this person here in the class? Artikov Sharuz, type or speak, please. All right, let's get to. Of course, I take attendance. Did you know that? I might actually start taking attendance in a more interesting way. I will ask a question, and on Blackboard, you will have to answer that question. It will be like a code to know if you were in the class and present at all times. So here is the solution, guys. So 3 plus h squared minus 9 over h. What happens here? So first I can expand 3 plus h squared, getting 9 plus 6h plus h squared minus 9. The 9's cross out, and I'm left with 6h plus h squared over h. I can factor out the h. Cross it out, you have 6 plus h. Limit will be 6. And everybody who said limit is 6, let's say how many people said that. Well, quite a lot. Not everybody responds, but okay, quite a lot. Okay, guys, here is the next situation. As it happens, we will establish this result much later in this course, but as it happens, the limits also work pretty well through radicals. You see, if you take a limit of a radical, that's now algebraic. You understand? That's yet another operation. When I take roots, then I am using something in addition to addition and multiplication and division. So that's the biggest category you have seen so far. And algebraic functions, those that allow you to use addition, multiplication, division, and roots of all types, they also behave rather well under limits. Okay, that's the biggest category. Do you see? If I have algebraic functions, that includes everything that we covered so far. Because you see, with each new step, you're adding more operations that you are allowed to be using. Yes? So algebraic is the biggest category. And limits behave pretty well under algebraic when you take algebra. Guys, let's see how good you are at this limit. Limit as t goes to 0 of root of t squared plus 9 minus 3 divided by t squared. Try to calculate this limit. See if you can do that. Li Zilong. Li Zilong is Li Zilong here. Type in the comments or speak. Jet Lao or Luo Jet. Thank you. Kasim Mariam.
Here.
Thank you. Raman Marva. Rivas Brianna.
Here.
Okay, thank you. Vildan. Rebihik Vildan. Okay. Ready? Zakaria Hussein, I didn't miss you by any chance? Hernandez Serrano Maricarla. Maricarla?
Yes, I'm here.
Great. Hassan Junaid. All right. Back to our little thing. Some people already answered it, guys. So let's see what we can do. One thing, of course, we can complete the squares. That's what it's called, or multiply by the conjugate. You see, I don't like to see the root. So what I will do is I will take this expression and I multiply it by the same expression, but with this minus replaced by a plus. And to simplify, I mean, I cannot change the expression, so I do the same for the denominator. Do not do anything more. I only did it for the numerator, so you do not simplify in the denominator. Yes, Humira, similar to how we do with complex numbers. The reason for that is you just know that you can get a squared minus b squared by writing it as a plus b, a minus b. That's the reason. They call it multiplying by the conjugate. So what happens here in the numerator? It just becomes the first number squared minus the second number squared. You understand? That's why we did it. So it's t squared plus 9 minus 9. Don't simplify anything in the denominator for now. You only did it for the numerator. The denominator part is your payment. You do that only so that you maintain the same expression. And then what you are left with is simply t squared divided by t squared. You can cross it out. So you have 1 over root of t squared plus 9 plus 3. T approaches 0, so that would be 1 over root 9 plus 3, which is 1 over 6. Every single person that answered, I believe, has answered correctly. But how many we have? 1, 2, 3, 4, 5, guys. 5. You should answer it all and very fast. Second row? What second row? You mean this part? It's just simplification. 9 minus 9 is 0, so you have t squared. It's just simply this. So there is a t squared and here is a t squared. And I can cross them out. And I'm left with 1 over, so I'm left with 1 over root t squared plus 9 plus 3. Right? Here is another one, guys. Try this one and let's see if we do more. We should not have 5. There are 27 people here. It should be 20 answers, I think, at least. So this thing, calculate the limit. Whitaker Moesha. Fang Liu Jian Yi. Wonderful. Okay, 2 people. 3. Is it the same question? I mean, the answer might be the same, but it's a very similar question, true? So guys, if at some point you don't solve it very fast, you can stay with me after class. We can practice more questions. Good? Okay. Yeah, well, it's the same question, true, you're right. But I solve it using a different strategy. See, I didn't notice. So you see that here is a different strategy. I will actually right now not go through the explanation of the different strategy. Okay, I will tell you about it later. Okay, so we move to continuity, guys. So do you see limit laws? And then there is precise definition of limit. Okay. So let me just open it up for a moment and show you what I am skipping. 16 pages. I'm skipping something that I want you to understand. It's just I don't have time to cover it in class, and it will be an extra credit question. You see, I'm trying to show you how I think of limits and how you can make it precisely. Make it precise. Your goal is to prove the limit laws. They are not just arbitrary statements. They are things that you establish and prove if you're a very good student. Okay, you see here is the water jet not entering the pipe. Here it's beginning to look like it will enter, and here it's entering. So I'm squeezing the domain until the water jet enters the pipe. And I go through this long discussion of how you describe it using the symbols of delta epsilon and how you prove that limits exist. And at the end, I show you some basic examples there. And at the end, I show you the limit laws, or at least some of the limit laws. You see, that is the limit of the product. You have to prove that if we have one function approaching L, the other function M, the product will be L times M. And this is not just something that we might have an intuition for it, but it's something that requires proof. Not only for those conditions, but if you go into higher mathematics, pretty much any statement is very frequently in terms of delta epsilon. Okay, so you have to understand it pretty much like when you read certain vocabulary. All right, so I will skip it and go into continuity. Okay, guys. So the question is, how can we mathematically define the idea that some curves can be drawn without lifting the pen from the paper, and other curves cannot be drawn this way. Okay, so we will think of a function f of x as continuous if its graph is one piece. You understand? So a lot of you associate, if you remember graphs, you associate this curve with the function. That's not exactly correct. Okay, so for instance, when you say, for example, we have the function f of x equal to x squared, a lot of you, I'm sure, picture this shape. Okay. Now, what is this shape? This shape is not this function. This shape is the expression x squared. This is the set of all points where the first coordinate is a number, the second coordinate is the square of that number. What this function is doing it's an action of one number line. It's an action on the number line onto itself. So what it actually does, it actually folds the number line at 0, folds it, and stretches it in some places. Okay, but the graph of the function can be one curve, or it can be several curves. So let's look at the following pictures, guys. So there is discontinuity, it seems, at the point x. Discontinuity meaning that I had to stop my motion and abruptly lift my pen to continue the drawing. So here, what happened? What was wrong? That I had to discontinue drawing the function at a. You see, what was wrong? It seems that the function is not defined. You agree? I cannot have a value f at a. Exactly. Right? F of a is undefined. We jumped. So we jumped through this, Christiana. We jumped through limit laws. Yes? We jumped through limit laws. That's all it is. You see, so the way it goes is here. 1, 2, 3 is what we jumped, and we're now in 4. 3 is the precise definition of limit. I don't like jumping over it, but you know, it will take me many lectures with you to do it. So it's posted on YouTube, and the lecture is there on my website, and it will be extra credit question on that. So you decide if you want to read it or not. Good. So you understand what happened here. Tell me what happens here. Here it's something worse. Look at it, guys. The function is defined at a, but it seems like I have to make a more abrupt jump. What happens here? Can you notice? Look at it. My left hand limit and my right hand limit do not match. Do you agree? Limit as I approach x, I approach a from the left, and as I approach a from the right are not the same. Yes? Okay, here the situation is different, right? What happens here, the limit from the left goes to infinity, the limit from the right goes to infinity. Neither the left or right limit exist. Well, wait, Francis, we'll see what kind of questions. Okay, for now we need to talk about this. Good, guys? So next is this situation. The situation describes what situation? Where is MA? What is MA into? G. Okay, so you mean G of A. This is just the number M that you get in the limit. Okay. GA, it's not, it could be constant. Yes, it doesn't matter. The limit is M. Good. So what happens here, guys? Here we have a nice limit as we go to A from the right, we get the number K, but as we walk on the left, we oscillate forever. So here the left-hand limit diverges by oscillation. In all those cases, I can see that limit does not exist, correct? And here, as I just described those same things. Okay, so which of those is the least terrible type of discontinuities, do you think? Which of the graphs, 1 through 4, do you think is the least terrible discontinuity? The least terrible disruption of... Yes, so you can see 1. 1 is the least terrible disruption, and what is 1 expressing mathematically? The limit exists. You understand? If the limit at A exists, then the disruption cannot be too terrible. And if the limit exists, we will call it removable discontinuity. It's just that one point was removed, right? Removable discontinuity, meaning that essentially it's very close to being continuous. Okay? So let's now try to define this idea mathematically, guys. Okay? Are you seeing this? So in this case, here is a curve where we are defining continuity at each point separately. This function is continuous at the point A for the following reason. Look at it, guys. If I trace with my pen from the left, or if I trace with my pen from the right, they merge in the same location. Do you agree? For it to be continuous, they merge in the same location. And also that location there, it's fused. It's fused. That location is f of a. The function is defined to equal that location. So we define a function to be continuous at the point A if the limit of f of x equals to f of a. That means both the left and the right hand limit exist, and they match the same value as the function would be at the point A. Do you understand? So from the algebraic point of view, a function is continuous at the point A if taking the limit produces the same result as plugging in A. You understand that? And do you see what this is saying? Look, guys, so whenever you think that you calculate limit by plugging in a number, what you're truly saying is that if it works, that the function is continuous at that point. You see? The curve merges in the same location. That means left hand and right hand limit are the same. And that in particular means they exist. Do you understand the definition, guys? It's very easy, I hope, right? Do you understand what it's not only what we are saying, it's also what is it that we're trying to say. Okay, what's the idea that we're trying to convey? Good? Or are you bewildered by what I just said? You're not bewildered yet, yes? It's all clear, right? So you see limit equal to the plugging in means the function is continuous at that point. And you see what motivated it. It means that we have a smooth motion. Where we go is where we end up. Good. Okay. So let's consider those questions, guys. So we asked the question, where are each of the following functions discontinuous? Let's begin with problem A. Where is A discontinuous? Okay. Good. When x is equal to 2, do you agree? Because plugging in 2 does not produce a result. So the function is undefined at 2. That already makes it discontinuous, but let's say a little bit more. Is it a very bad type of discontinuity, or it's just like a bump on the road, just one point where we are having problems? So let's look at question A. Yes, exactly. So it's a removable discontinuity. Do you see why it's removable, guys? Look what happens. I can factor x squared minus x minus 2 over x minus 2. Do you see it? I can factor it out. And when I take the limit, I get the number 3. Are all of you getting it? X squared minus x minus 2. Factor it out. It's x minus 2 times x plus 1 divided by x minus 2. And x minus 2 is simplified. We take the limit, we get 3. Yes? You remember how to factor, guys. Do you understand that? Another thing you should know, my friends, is that you see, we go slowly to try to allow you the time to catch up with prerequisites. I should not be stopped on any algebra, right? I am, of course, hoping that you can ask me questions, any questions, no matter from what level, and I'll try to explain. But you need to work on it yourself. You need to stay after class if you cannot do those things that are considered given, you know? If we're teaching Hamlet, if we're going through Hamlet, I cannot tell you what's the letter H. I will, after class, of course. So don't right? Don't hesitate to ask me anything, but you have to help me. So x minus 2 times x plus h, and when we cross it out, the limit is 3. Good. So the fact that the limit exists means we have a removable discontinuity. Now the next part is b. We have 1 over x squared. The function is defined to be f of x equal to 1 over x squared if x is not 0, and 1 if x is 0. Tell me what goes wrong with this function. Where might it fail to be continuous? And what type of discontinuity do we have? Removable or not? Careful, Robert. At what point of x is it discontinuous? Maybe you're mentioning the 1 in the range. But you have to speak of the domain when you talk about continuities. Come on, guys. So why does it take any time? What happens here in B? We take the limit as x goes to the value 0, right? So for any value, it's a rational function. So at any value where denominator isn't 0, the limit is the same as plugging in the value, right? So it's continuous everywhere except at 0. Do you agree? You look bewildered. Look at this expression, guys. Limit as x goes to the number a. A is just any number. I'm assuming a is not 0. That's the only thing I'm assuming. Of 1 over x squared. This is the limit of the quotient. So it's 1 over limit as x goes to a of x squared, which is 1 over a squared, which is the function, right? So this is the function evaluated at a, which means we have continuity, right? We have continuity at every point that's not 0. But on the other hand, if I take limit as x goes to 0 of 1 over x squared, what am I going to get? I'm going to get 1 over 0 plus, yes? And that means 1 divided by ever smaller positive fractions that are close to 0. And the result is infinity. Do you all understand that? You see, guys, another thing, I mean, you are not all of you comfortable with multiplication. And not all of you are comfortable with division. And again, I can show you how to do that even geometrically. I want you to think very deeply about those ideas. Why dividing by something close to 0 gives you infinity? I can show you that geometrically. I can show you that or try to explain it algebraically, but it has to be extremely clear. When you divide by very small numbers, if you divide 1 by a very, very small number, you will get a huge number, okay? You have to have a feeling for that. Okay, I can give you a geometric feeling. So the answer is here is plus infinity. So the limit the limit does not exist. Do you agree? Plus infinity means neither the left nor the right limit exists. So right away, the function is discontinuous. You understand what happens here? It means that the graph is getting ever so steeply up from both directions, from 0 minus, from 0 plus. That means it's torn at the point 0, no matter how it's defined at 0. Good? Do you understand, guys, right? Because I'm asking again because I haven't seen too many responses to this question. It should be immediate. So the answer is infinity. Now this question C, I will quickly mention, it's the same as A, but notice I redefine it to be equal to 1. I would say that it's still the same thing. It's just removable discontinuity because the limit is 3, but the function is not correctly defined. But yeah, so I would have said that it's a removable discontinuity. Of course, because the function is defined at 2 to equal something, some people might say something else, okay? But the idea is simply, the main idea is this. If limit exists, it's not a very bad discontinuity already, right? If the limit exists, it's essentially continuous. Good? Here is the next next function, guys. Do you know what is the greatest integer function? Let me just, it's a very important function, actually. I can show you some very cool applications of it in physics. So the greatest integer function rounds the number down to the nearest integer, to the floor, okay? So for example, if you take, I'll use that symbol. What do you think is what is 3.1? The greatest integer function of 3.1 is 3. You fall down, you understand? What is 3.999? What's that? No, you don't jump up, you always fall down. Imagine that you are between floors. You are between the 3rd and the 4th floor, and gravity will drag you to 3. Okay? No matter how close you are to the very top, it's almost there, but the gravity will drive you down to the floor, to the floor at the bottom, okay? Now, of course, naturally, the greatest integer function of 2, you're already standing at the floor, so it will be 2. Tell me, please, what about this, guys? Minus 0.01. What is that going to be? Minus 1. You are at the basement, and there is a floor below the basement, sub-basement. So you fall down to minus 1. Yes? Good? So the question now is, where is the greatest integer function discontinuous? Okay, where is the greatest integer function not continuous? Careful, Christiana. Do you understand my question? Yes, guys? Where is this function? You know, if I were to draw the graph, you don't even need to see the graph, but I'll show you both ways. Yes, good. Good, Christiana. Yes, guys, I do think you have those faces that make me need to teach you constructible numbers. I need to show you how that is done. It bothers me. All right. It's very simple. Here is what we do, guys. Okay, so I drew the interval this way, but you can imagine drawing it vertically if you prefer. Okay, so the question is very simply, at what values will the limit be the same as plugging in the value? Okay, so pick limit of the function at the number a. Okay, maybe I'll do first one example where a is actually a number. You cannot do it forever because you have to speak of all of them, otherwise you will never finish the discussion. So if my function is the greatest integer function, will it be continuous at the point 2.1? Okay, will it be continuous at this point? So what I do is I ask, first of all, what is going to be my limit? So first of all, 2.1 is between the numbers 3 and the number 2, right? 2.1 is between 3 and 2, so it's somewhere in here. Good? So it means that I suspend my figure in between second and third floor. And then I ask what's going to be the value of f at 2.1. The value is clearly just you fall down to the second floor. Yes? Now, what is going to be the limit as x goes to 2.1 of f of x? What's the limit? The limit means what? The limit means I plug into the function numbers that are extremely close to 2.1. You agree? If they're extremely close to 2.1, then they will be kind of in this neighborhood of 2.1, right? Maybe a little bit more, a little bit less. In this red region are numbers that are close to 2.1. All the numbers in this region will fall down to the number 2. Do you agree? All those red numbers, those are imitations of 2.1. All of them will fall towards 2. So, which is what? Which is f of 2.1. So the limit at 2.1 is the same as plugging in 2.1. Therefore, the function is continuous at 2.1. Do you see that? Yes? Notice I could draw the graph for this particular, I can draw the graph of this function, but that's a very kind of limited reasoning. You should be able to have this algebraic sense, or just without actually drawing, seeing what happens, right? That means, in other words, no matter if you place a figure between the second and third floor, or at one particular point there, or at a point very close in between, it all falls down to the lower floor, right? So that is going to be true anywhere. Let's just prove that it's not just true for 2.1, but for any number that's not an integer. Okay, so pick a number a that's not an integer. You remember what z stands for. Z is Zahl, which means number in German. So pick any number that's not an integer. Then this number that's not an integer is between some integer n and the integer n plus 1. What's going to be the value of the function at that a? It's going to be n, right? F of a is n. Do you see that? F of a is n. And what is the limit? The limit means that you're slightly above or slightly below, you still fall to n. So the limit from the right or from the left will simply be n. Good, so that means in particular that for any non-integer, the function is continuous. Do you see that? You say, I cannot go and say 2.1 and 2.7. I have to speak of all the numbers that are not integers simultaneously. Otherwise, I will never be able to finish my conversation. Are you with me, guys? You have this frozen look, like you are in perpetual hell. Yes. Good. And now pick an integer, right? If the function is an integer, if the a, sorry, is at an integer, then what happens? Let's draw a picture. So at an integer, let's say at 2, so let's say f of 2 is equal to 2. But what about limit as x goes to 2 plus of f of x? What would that be equal to? What limit as I approach 2 plus? What's the limit, please? Exactly, that's 2. In other words, if I jump slightly higher than 2, I fall back down to the floor 2, right? But on the other hand, what is the limit? So look at it. This means right continuous. If the right-hand limit equals to the function, that's called right continuous. You see why? The limit from the right is the same as plugging in the numbers. So the function is already right continuous everywhere. Is it left continuous? So limit as x goes to minus of f of x is what? One. The answer is 1. Yes? Good. Good. The answer is 1. So that means that the function is not, look at it, it should have been equal to 2. So the function is not left continuous, right? The limit at the left fails us. Yes? Good. So we just examined some basic continuity problems. Now, this is slightly boring problem what I'm presenting now. First of all, guys, f of x equal to 1 minus root of 1 minus x squared. What classify this function? It's what? Is it polynomial? Is it something else? You see, we look at the operations we're using here. This is called a what type of function? Well, there is a square root, but the species of those functions is known as algebraic. It's an algebraic function. That's where you use addition, multiplication, division, you can use if you want to, and taking all sorts of roots. Yes? So it's algebraic function, and we can show that this algebraic function is continuous on the domain of its definition. Yes? So we take limit as x goes to a, where a is between -1 and 1. We just verify it's continuous between -1 and 1. We take the limit as x goes to a. And what happens here, guys? Well, I can do this by the limit laws. You see, I just carry out, there's a limit of the square root of the square root of the limit. And at the result, I end up with 1 minus root of 1 minus a squared. So this function is continuous at every point between -1 and 1. Yes? Now, similarly, I can calculate for right continuity at -1. You see, we see what happens if I approach -1 from above. And it will be the same. And left continuity at 1 will be f of 1. So it's continuous everywhere. Here is the theorem, guys. So just like mirroring limit laws, it's following exactly for the same reasons. If you have two continuous functions, f and g, the sum of those functions, the difference of those functions, a constant times a function, and the product will all be continuous. The quotient is continuous as long as the denominator does not produce zeros. Okay? So there is a very easy way to generate more continuous functions once you know certain continuous functions. So here is again what we make this remark, guys, that polynomials and rational functions are continuous at every point where those functions are defined. That means that they are particularly simple when you take limits. Okay, now what's the reason for that? We already verified the reasons, right? We know that applying limit laws for product, addition, subtraction, whatnot, then we will have that polynomial evaluated at a is the same as the limit. For rational functions, we introduce the quotient rule. The quotient law tells us that the limit of the quotient is quotient of limits as long as denominator isn't 0. Okay. Now, first theorem. Actually, this is a theorem beyond our ability to prove in this class. You need to know the concept of intactness, what it means for something to be intact. I can teach it to you, but you will need some other ideas for it. Okay, but this theorem is true for real numbers. Suppose that a function is continuous on a closed interval AB. You see there is the closed interval AB. You know that the function is continuous. And take any number capital N that is between little fa and little fb. Okay, like in this picture. We're assuming that f of a is not equal to f of b. So there must be a solution to the equation f of x equal to the number n. In other words, look at this curve. If I know that the function is continuous, but I do not see the curve, I can connect this point to that point. I just do not see the connection is invisible. There is an invisible string that connects it. So the idea of this theorem is to claim that the invisible string must cross this river. The invisible string must cross this horizontal line at least in one point, maybe in several. Okay, can you see it? So a lot of people have, that's the first major problem, is that a lot of people do not even have a visual for this theorem. Okay, so let me try to show you what's the use of this theorem, at least some example of it. We will see many more. So suppose that you want to understand whether or not 4x cubed minus 6x squared plus 3x minus 2 equal to 0 has a solution, right? Maybe between the numbers 1 and 2. Okay, clearly this equation is not always equal to 0. For example, if I plug in 0 instead of each x, I just get minus 2. You agree? Plugging 0, I get minus 2, which means that I'm not always getting 0. Now, will I be able to get 0? Here is how I can think of this problem. Are you ready? So I can define the function p of x equal 4x cubed minus 6x squared plus 3x minus 2. It's a polynomial. And now I know that polynomials are continuous, which means even if I don't bother drawing its graph, I know its graph is going to be an intact curve. It's going to be one string intact. Can you see that, guys? That's what we were talking about. Continuity is the idea of if we know that the function is continuous, it means that its graph is intact. Good. So the thing is, I do not draw it, so I don't know how the graph looks like. But I observe the following. I observe that at the point 1, if I plug 1 in here, I made 1 point visible. I have the point 1 comma minus 1. So in other words, at 1, the graph dips below the x-axis. It's less than 0. You see? At 1, I don't get 0. And at 2, if I plug 2, I get 12. Plug in 2 here, you will get 12. And 12 is a number bigger than 0. So you see what I'm saying, guys? Look at it. You are below sea level and you're above sea level. That means that there must be a moment when you cross the x-axis. And when you cross the x-axis, that's the solution to 0. That's exactly where you are equal to 0. Maybe there are many moments like this, but there is at least one. That's what the intermediate value theorem is claiming. Do you understand? Let's see with another example. Okay, are you ready? This one is a little bit more difficult, but let's see what you will do. Okay, so show that the equation cube root of x equal to 1 minus x has a solution, has a root, which means what you're seeking for, guys. Do you understand what this is saying? Can I find a number that if I take the cube root of it, it's the same as 1 minus the number? You understand what the equation is saying? Is there a number whose cube root is the same as 1 minus the number? And then we will see how we can claim that such a number will exist. By the way, guys, if you feel stuck or defeated, some people, they don't get something right away, they have a very low threshold for frustration. What you do, you stay after class with me, we can discuss it at your pace, and I can answer your very specific questions. I hope you understand that. Okay, so just resist the urge to leave, and I will help you. Let me give you a hint with this problem. It's always easiest to compare against 0. So you always want to move all parts of the equation to one side, because then it's always something equal to 0. Okay, that's why solving the equation to equal 0, why do you care about such things? Because it's the easiest thing to compare. 0 is between minus and plus. So comparing to 0 is easy. Okay, so move everything to one side of the equation and then try to make your argument. Yes, exactly. You can move or the other direction. It's up to you. Always compare to 0. That's always going to be easier. Yes, Abhishek, but we are not dealing with a polynomial. What we have here is cube root here. Yes. We shall. I'll wait one more minute, guys, and then we will see how that works. All right, are we ready? Let's go together. Second. Okay. Here we go. So here is what I suggest doing, guys. I suggest comparing to 0. So move, first of all, everything across the equal sign. The minus x becomes a plus x, the 1 becomes a minus 1, and I reduce the equation to cube root of x plus x minus 1 equal to 0. They are exactly the same equations. If I can solve one, I solve the other. Good? So then I define this to be my function. F of x is the cube root of x plus x minus 1. Yes, guys? And then I wonder whether or not I'll be successful in, well, this function is first of all continuous. I hope you see that, right? It's an algebraic function. Algebraic functions, whenever you take the limit and, you know, at a value where you can plug it in, it will work. So the function is continuous. Plug in 0, you get minus 1. Plug in 1, you get 1. You see that? I plugged 0. I just plugged something that gives me a value that's less than 0 and something that gives me a value more than 0. If I can get such two values, then I know that the curve had to cross. Because if the function is continuous, the curve is intact. So if part of the curve is below the x-axis and part of it is above the x-axis, right? There must be a crossing through the x-axis. That's the idea of the intermediate value theorem, okay? So I say at 0, it's below the x-axis. At 1, it's above the x-axis, which means by the intermediate value theorem, there is at least one crossing, at least one number c, which gives you 0. Good? At least one number c that will give you 0. Do you understand the idea of this theorem, guys? So, any questions? Okay, we will see how it is. I mean, if you want to understand, let's say, existence of roots and whatnot, all sorts of things, I can show you that later on as we learn more about the material. I can show you that it plays a big role, right? And continuity is related to the idea of connectedness. So for instance, I like to speak of this creature called homotopy, if you want an idea for a movie. And this homotopy, it's a sort of fungus. And what it eats is holes in space. And what it does is basically like a plant. It grows out and launches a hook and tries to wrap around a hole in space. Right, and basically then pulls this arm into its body, and it melts into its body. You see that's a creature that behaves by the rules of continuity. If you are made, basically, if you're not sure if you understand me, if you are made of a fabric that can be distorted by continuous functions, you will have certain interesting properties. You could take, let's say, your arm. You could push it through your stomach and you'll be okay, right? But once you put it into your stomach, you are stuck. You will have to melt your arm into your body and grow a new one. So those are the operations that that you use to study the structure of space. You create this type of fungal creature that will spread its tentacles around space and try to grab around the different holes in space. That's called homotopy. So if you're interested in this, I can describe it more. It's pretty interesting creature, feels biological. And it has tentacles, anti-tentacles. And when you do the algebra on it, you are actually describing the structure of space. All right, so whatever, if you didn't understand a single word of it, and that's just hopefully meant to excite you that there are very great ideas behind anything that we're talking about. There's potential. Let me ask you this question, which we will answer during the next lecture, not right away, during the next lecture. Yes, guys? So this is the question. Ready? Think about it very carefully. So we have a Tibetan monk, and this monk leaves the monastery at precisely 7 a.m. and takes his usual path to the top of the mountain, arriving at the top of the mountain at 7 p.m. Good? That's one day. The following morning, he starts at 7 a.m. at the top and descends from the mountains along the same route, arriving at the bottom, back to the monastery, at 7 p.m. Okay, and you recorded both videos. You were traveling with this monk and you recorded the video on day 1 and you recorded video on day 2. You understand? The question is this, and then you play those videos side by side, and this is what you have to show. Explain or prove that there is a moment of time on day 1 and the same moment of time on day 2 where the monk is exactly in the same place on the mountain. So there will be in both days, the monk will be in the same place on the mountain, at least for one moment of time. And here is the picture for it, you understand? You recorded the monk. The monk initially was at the base of the mountain and he was climbing to the top. And on day 2, at the beginning of the video, the monk is on the top of the mountain. The duration of each video is the same, from 7 a.m. to 7 p.m. Do you understand? Your goal is to show that the monk must be in the same place at the same time in both videos. Question clear? And can you do that without too much mathematics? You understand, guys? So it's not that you have to have X and Y's and whatnot. It's just can you come up with, can you notice patterns? Can you see what might be a simple way to imagine why that statement is definitely true? We can prove it, but why would you imagine the statement to be definitely true? Do you first understand what the question is asking, guys? Yes? Do you agree that at 7 a.m. the monk is not in the same place on both days? You agree? At 7 a.m. In one video the monk is on the base of the mountain, in the other video the monk is on the top. Okay, so you have to find a moment where they are in the same place. And of course, don't assume the monk is walking the same way. You don't walk the same way on each day, right? You can walk, you might forget your hat, you walk up, you walk back up, and then you begin descending. You understand? You can go up, down, you can walk as wherever you like. You must only be in both videos. The first video you have to be at the base of the mountain when the video begins and at the top when it ends. And in the second video you must be at the top when the video begins and at the bottom when the video ends. Yes? Clear? Wonderful. All right, guys. So this topic we will cover during the next lecture. Yes? And that's and what I mean is that I would really like you to think we are taking a break until not right away. Don't leave. We have another hour more or less, right? Don't you escape. We have a very interesting lecture coming on. But before we go to that next lecture, guys, let's take a moment pause, and I will show you something I prepared for my probability students. All right, but it's from that my favorite game. So we're gonna play one round of what, when, where. Okay, before we continue with the next topic. Are you ready? Yes, I hope you're happy, guys, because, you know, by the end of my goal is not just the mathematics. By the end of this class, you will be waving a Soviet flag over the capital. You understand? And speaking Russian. Okay. I'll pause the video, and this will be an attendance. You see, so that would be one way I'll check if you came to this class, if you know which, what, when, where question I asked. Okay. Okay, if you have, guys, you're not in prison yet. It's not the gulag. We haven't taken control. All right, guys, and we're back. Welcome back to the math. We are having a very interesting topic that begins right now. One of my horrors, my internal nightmares begins now. So first of all, let me be very generous to you. Right, here is a question that I call Arcadis generosity problem. Right, we're going to play with infinity, and if you want, I will give you the following prize. So I will give you $2 and $2 squared dollars and $2 cubed dollars and $2 to the fourth dollars and $2 to the fifth dollars and $2 to the n dollars and so on, right? I will give it to you if you ask me. Who would like to get this prize. What's the catch? Why are you assuming there is a catch? Do you understand? 2. No, it's I am very truthful. I never lie to you. Yes, you will get what you ask for. You will. That also relates to a very good book that you should read. It's called Master and Margarita. Hopefully translation is good for it. I will send you information about this book in the email. So, do you understand my question, guys? Right? You can get $2 plus 2 square dollars plus 2 cube dollars plus 2 to the 4th. You can get all the sum. It goes to forever. All of it you will get if you just ask me. My God, what is it done? So the fact that the Democrats won made you no longer love money, I think, huh? Is that right? Communism has been instated. Good. What's going to happen, guys? So you're too quiet and petrified. Interesting. My God, that's you're so suspicious. So you have a feeling, or do you know? So let's see. You should think this way, guys. Right? If you want it, you like the word "it." What is it? What will you be getting? Okay. So will you be getting something? So if you are getting something, the answer is, well, let's set it up, right? So you're getting something. Let's calculate. You're getting something, correct? Something is equal to that weird looking thing. It's one pile of $2, another pile of 2 square dollars, 2 cube dollars, 2 to the 4th, 2 to the 5th, etc. Right? And then let's look at this pile very carefully. Do you see that what I placed in the red parentheses looks very similar to the original sum? Do you agree? Because it's unending. You agree that what I placed in parentheses, it just starts with 2 squared, but other than that, it looks like the original sum. What do I do to figure out what that original, what this thing is? Oh, I can factor out a 2. Do you see that, guys? I factor out a 2 from all of them, and I have now 2 plus 2, and here we have the original sum. So the sum equals to 2 plus 2 times the original sum. And I reduce the problem to complexity. I reduce the complexity of the problem to the statement that the sum equals to 2 plus 2 multiplied by the sum. Yes? Are you with me? Yes. So that means that, of course, I mean, I don't know, you were petrified, I guess. I'm not sure why you had no reaction. That means that the amount of money that you will be giving me, or that you will be getting, is -2. So that means if you volunteered to receive this, you would have to pay me $2. Good. Now, you might wonder, okay, this is a bit wrong, right? Because let's look at it again. What's going to happen, right? Another solution to this equation will be infinity equals to 2 times infinity, right? So you might wonder, maybe I am lying to you. Maybe, in fact, you are getting infinity. Good. Like infinity will be 2 plus 2 times infinity. Definitely, this is what happens if the amount that you will be getting is finite. But maybe it's not finite. What should it be? Right. So what you have is that I will try to explain a little bit is that nature does everything it can, it seems, to prevent infinity from coming to be. You understand? So in physics, when you study physics, you realize that if you have 2 solutions and one of the solutions is infinite, the infinite solution somehow must not happen, must not be. Okay. Another thing you might notice is in terms of limits, that's especially if you take Calc 2, is that if you get $2, if I give you a pile of $2 and then I give you a pile of $4, you gain money. And then I give you a pile of $8, you gain even more. And a pile of 2 to the to the $5, $32 and onwards, right? You're gaining. If I'm giving you the piles one by one, you seem to be gaining money. But if I give you all that sum, everything, it might mean that you are actually losing. Okay. Here is an example of what I mean about infinity. Okay. So physics begins here. So you have two astronauts. They're pulling on both sides of a rope, and the rope is of mass 0. The rope has no mass. Imagine you have some sort of strong rope, but it has no weight whatsoever. Okay. What can you say about the relationships of the forces, right? So one astronaut might be very strong compared to the other astronaut. One astronaut is super muscular, the other astronaut is scrawny. Who do you think pulls this rope hardest? You see, they're pulling at this rope. Which astronaut is pulling harder, do you think? Which force is stronger? So you imagine two astronauts, they're pulling on the rope. The rope has 0 mass. What is the relationship between the force applied by A and the force applied by B? Which force is bigger, you think? Let's say A is a stronger guy than B. Guys, do you need a restart? You look frozen. All right. So let me again. You see, guys, it is surprising if you have expectations. If you have no expectations, it's impossible to surprise you, right? So here is the situation. As it happens, they cannot apply different forces on the rope. They have to apply exactly the same force on the rope. It's impossible for them to not match in forces. So what happens, and that's very important, I mean, that's how you solve most problems in physics. You have to understand this principle, is that the difference of forces, Fa minus Fb, will be ma, will be the acceleration in this direction. Now, if the force Fa is bigger than Fb, then there is a positive net force. But since m is equal to 0, 0 times a, unless a is infinity, will be 0. So you understand? So m is 0. And mass is 0. Force, the difference of forces is mass times acceleration. Now this quantity, because mass is 0, has to be 0. That means that Fa has to be equal to Fb. Unless, of course, you might have say the only thing that can struggle against 0. Look at it. Multiplication by 0 is very important here. Do you agree? Which I don't feel that all of you understand what it is. Multiplication by 0 makes it 0, which means that the forces have to be the same, unless the only thing that can possibly compete against 0 is infinity. But infinity is not supposed to be happening experimentally. It seems that nature will do everything to prevent infinite acceleration or infinite anything. Okay, so that tells you that the two people can never apply different forces on the rope. Next part, guys, is this is the way you record summation. It's a sigma notation. It means you go from K1 and then K is updated to 2 and then K is updated to 3 and onwards, and you put it in sigma notation. That's the same thing here. It's just much more compact to write it this way. Okay, can you try to put in sigma notation? You can just write sigma, bottom is what K equal to, top is what K equal to, what's the summation of 1 over 10 to the 1, 1 over 10 to the 2, 1 over 10 to the 3, and onwards. What's that in this notation? Let's see if you get the notation just before I talk about it later in the course. You understand what is that sigma notation, guys, or you missed it? So let's see. Again, guys, this is just a notation to describe summation of this form. It means what? Wherever you see the k, that's the thing that's updated by 1 unit up, right? So look at it. If I see the k here, it's 1, 2, 3, etc. I can write it as sigma k equal 1 to infinity, and here I write ak. So then in sigma notation, let's see who answered it. Yes, k begins from 1, then it goes to 2, etc. So in sigma notation, this can be written as 1 over 10 to the power of k. Okay, and yes, we're going to learn a lot about it later in the semester. This notation is just, instead of writing it lengthily like this, you can just write the symbol, which means sum, all the terms where this index goes from, this is the first number, all the way to this number. And that means 1, 2, 3, the index will upgrade until it reaches n. So here the index is the power of k. So it's the power of 10. Good. Here is a question here, guys. So in your calculator, when you press 1 divided by 3, have you ever pressed in your calculator 1 over 3? And what you get is 0.3333. What does it mean? What is that 0.333? What is 0.333? It means what? Continuous, Humira, it's wrong word. You mean not ending, but what is that? What is the 0.333 represents?
3 over 10.
Yes, and then the next one is 3 over 10 squared, and the next one is 3 over 10 cubed. Okay, guys, we do need to work on your knowledge of numbers here. So look at it. So it's 3 over 10 plus 3 over 10 squared plus 3 over 10 cubed plus 3 over 10 to the fourth. So when you see those fractions in your calculator, what it represents is an unending sum. Do you see this? Forever. So it's claiming that 1/3 is the same as 3 divided by 10 plus 3 divided by 10 squared plus 3 divided by 10 cubed and onwards. Clear? Let's try to verify that it's indeed the case, just like we did for the for my previous question. Okay, let's look at it. So I can set the summation is 3 over 10 plus 3 over 10 squared, etc. It looks like well, like we just call it the summation. We call it S. And what I put in the red parentheses, look at it. I move beyond the first term, and what I place in the red parentheses looks almost like the original thing. Do you see that? Do you see that the thing in the red parentheses looks like the original thing with minor difference? That you have to notice, guys. Pattern recognition. Do you see? It begins with 2 and then goes to 3 and then goes to 4. If it were to begin with 1, it will be the same thing. So what do? I factor out. That's what I do here. Look at it. You see, I factor out 1 over 10. Because when I factor out 1 over 10, you see what happens here? It's now 2 minus 1, 3 minus 1, 4 minus 1. So 1 over 10, 3 over 10, 3 over 10 squared, 3 over 10 cubed. What I have in the parentheses is exactly S. You see that? Right, you look confused. I do not know why. So we have S equals to this expression. So then I can simplify the expression. It means that S equals to 3 over 10 plus 1 over 10S. Yes, you see what I did, guys? It's just a pattern recognition. I try to avoid the scary looking infinite sum and make it look like some very easy equation. So if this is a number, it's equal to something. So something is equal to 3 over 10 plus 1 over 10, the same something. Now I move this across. So S minus 1 over 10S, look at it. S minus 1 over 10S equals to 3 over 10. So that means 9 over 10S equals to 3 over 10. Look at it. So then I can simply say that S equals to 3 over 10 multiplied by 10 divided by 9. And the answer is 3 over 9, which is 1/3 indeed. Yes? It is 1/3 indeed. Let me check that you understand what the summation is. I'm going to give you a number, a sum, and you will tell me what it equals to in fraction. Good? So tell me, please, what is 7/10 plus 7/10 squared plus 7/10 cubed onwards? Tell me, what is this equal to? So I mean, I have here 0.7777 forever. You can write it as 0.7 with a bar. So the 7 is repeated. What is that sum equal to, please? Okay, so 7/9, you say, Humira. The class is over at 3:30, correct? Okay, let's see what we have there. 5 people answered. Okay. Should be more people, guys. Right away. It's very easy, right? So what is the idea? The idea is this. You look at the scary thing and you ask yourself, is it equal to something, right? So why not? That's what you do here. You say it's equal to something. Good? What do you do next? When you say it's equal to something, you try to see whether it has a part of itself that's self-similar. So tell me what to do. Look at it. You see, guys, 7/10, and then I skip the first term. It's not always just skipping the first term. You see what I'm doing, guys? I just have pattern recognition. I just see what's in here looks very similar to the original expression. Do you agree? Except that the powers of 10, they don't start from 1, they start from 2 here. Yes? So what happens here? What would you advise that I do next? Red parenthesis, what would you advise me to do now? Take out 1/10, exactly. Do you see why? because if I take out 1 over 10, what will be in the red parenthesis, what remains in the red parenthesis is the same thing as the original sum. Do you see that? This is the original sum. Look at it, guys. So let's do that. So it's 7 over 10 plus 1 over 10. And then here I have 7 over 10 plus 7 over 10 squared and onwards. Yes? You see, guys, you have to have a strategy when you do those things. It's just nothing more than just strategy. What is our goal? You have to have a sort of bird's eye view. What is my goal? I look at this full thing and I recognize that it looks like the summation contains a part of itself. So this is also S. So then I have that S equals to 7 over 10 plus 1 over S. Sorry, plus 1 over 10S. Yeah? Do you see what I did, guys? I was able to reduce complexity here. And then I move the 1 over 10S across, and then I have what? I have 9 over 10S equal to 7 over 10. So that means that S is equal to 7 divided by 9. So it's 7 divided by 9. Are you with me? Let me check with another question that is maybe slightly harder. Shouldn't be harder if you understand, you see, the principle, not like this particular, it's not a baking recipe. It's not like you do first, second, third. That's not how you do mathematics. You just have to reason what is it that you're trying to figure out and what's your path to it. What is it that you pay attention to? So tell me, please, what is the number 0.232323 onwards equal to? Okay, here we go. Okay, David, interesting. Could be simplified, but yes. Humira. Okay, so good. So let's look at what it is, guys. So you can represent it in many ways. The nicest way, I think, for this problem is to say that we have S equals to 23 divided by 100 plus 23 divided by 100 squared plus 23 divided by 100 cubed. Will be the same if you represent in multiples of 10. It just this way grouping it much more conveniently. Okay, and then again I noticed this that whatever follows after the first term is very similar to the original summation, to the full original summation. So you understand, guys, that you to do mathematics, you're not thinking like you're following a cookbook. You're thinking philosophically. What is it I'm saying? I'm saying it's almost like in the Bible, or like the belief that is described in the Old Testament, is that the word is very important. Well, you think about Adam, and when all the animals were brought before Adam, he named those animals, right? What's the significance of naming? Is that when you name something, you have partial control of it. And if you know how to name something well, you can gain a lot of control over that thing. So there is something like this as well happening in mathematics. So you see this S, you see this? What I put in, what S is, it means that the summation, I named it. I said I'm getting something. Now, then I noticed that what I placed in the red parenthesis looks very much like the original something I'm getting. Yes? With slight modification. All I need to do is factor out a what? To make, what do I factor in this situation out of red parentheses, please? Exactly, it's V. You factor 1 over 100. So that is 23 over 100 plus 1 over 100. And then what I have in parentheses, look at it, guys. What's in parentheses is the original sum. So it's 23 over 100 plus 23 over 100 squared and forever on, right? So that's the point, is that this expression is just my original sum. And you can check in your calculator. So look at it. What happens now is that we have that S equals to 23 over 100 plus 1 over 100 S. And then if you move it across, S minus 100th part of it is 99 over 100 S equals to 23 over 100, which makes S equal to 23 over 99. Good? It's 23 over 99. So those that said that, that's correct. Good? Do you understand the idea? Yes. Let's see. Now let's do one more example to see how such ideas are important in probability. Very basic example. So suppose that Giovanni, what bothers you about the 99? So let's look at it. Where is it? The 99 is this. It's just if you take S and you subtract, look at it. You see this part? I move it across the equal sign. So that means I take S and subtract from it 100th of S. What am I left with? I'm left with 99 over 100, right? So if you take a cake and divide it into 100 parts and you remove 100th of that part, you're left with 99 parts. Okay, so then you get 99 over 100s equals to 23 over 100. And then simply you can cross away, they multiply both sides by 100, it's crossed, and then divide both sides by 99, and you have 23 over 99. Now here is the probability question, last question for today, possibly. You roll a fair die until either the number 1 or the number 6 comes up. You understand? So you continue throwing the die until you see 1 and then you stop, or you see the number 6 and you stop. Good? Understood what you do? The question is this. What's the probability that you stop with 6? You understand? You roll until you get either 1 or 6. So what's the probability it will stop at 6? Can you figure it out? It's a very simple question. You can solve it in so many ways. But what's the probability the procedure is stopped at 6? It means you haven't rolled 1, but you came up with 6 before you came up with 1. Okay. Zvi. No, not correct. You can try to see if you see the answer without doing any calculations, and then we will do a calculation. Okay. David, no. All right, let's do it together. So first of all, by symmetry, the answer must be 1/2, because you see there is no preference if it's a fair die which side is shown, right? Whether you see you have symmetry, either you play the game until you get 6 and you never got 1, or you play the game until you got 1 and never got 6, right? There is symmetry, the answer must be 1/2. Let's see that it's indeed 1/2 in the following way. I am not, of course, assuming you know probability, so if you understand nothing about this problem, that's okay. Okay, we're not talking about probability. I'm just trying to show you that some of those ideas are extremely useful. Okay, that I mean, if I teach you infinite series, I use that all the time. And if you do mathematics, you will use it all the time. So let's suppose that the game will be stopped on either the first row or the second row or the third row or the fourth row. In general, it will be stopped on the kth row. Do you agree? Where kth means first, second, third, etc. Right? Either I right away roll a 6 or I don't, and maybe the next round I roll a 6. Right? And before I didn't roll 1 or 2. So if it's stopped on the kth roll, that means that I played the game for k rounds, and the last round was victorious. I got 6, and before I never got either 6 or 1. There are 4 possibilities for each trial, right? So I cannot get in the first trial either 6 or 1. I cannot get it in the second trial, third, fourth, etc. So I get this formula. I get 4 divided by 6 to the power of k minus 1 times 1 over 6. And so my summation basically my probability of winning is to win either on first or second or third or fourth forever. All right. So in general, it will be summation from 1 to infinity, where the number of rounds approaches to infinity, and it looks like this. In particular, either I win on the first round, and that is 1 out of 6 possibilities, or I win on the second round. And that means on the first round, I did not get either 6 or 1. 4 possibilities for the first round, 4 over 6 probability of getting those 4 possibilities times the victory. Or 4 possibilities and 4 possibilities for the first 2 rounds and victory. So it's this summation. Yes? And once you simplify the summation, you see indeed that the probability is 1/2 as I claimed. Yes? So just before you go, just one small thing, just to illustrate the situation. You see, guys, so in the research that I was supposed to, that I was doing, I had generated this picture, and I had to prove a sort of, it doesn't matter what I had to prove really, but the argument that I have here actually involves an infinite sum. It involves an infinite sum. I can show you what it looks like. Basically, the argument for this paper involves that thing that you are that I'm trying to teach you. Here, let me show you how it looks. So you have this. You see, this is an infinite sum. And you have this other situation, and again you get an infinite sum there. So if you learn this topic very well, it will be a topic that you will use forever in physics, forever in mathematics, forever in pretty much anything. It's extremely potent. Okay, guys. So I thank you for staying so long. I know it's very difficult. If you want to talk in office hours, stay. If not, I stop the recording, and have a good vacation. You know, a weekend, I mean. And you can come in the evening office hours or in the evening class if you want to do so.